I will be a little faster, than the usual pace. Okay. And I mean, mainly what I want to do is twofold. I mean, the first thing that I want to show, if you want, how to prove the Weil positivity, assuming the trace formula. Of course, I mean, I will explain, where we were standing before, and then I will explain also what is a missing argument to justify the trace formula in the case of fields of positive characteristic. Okay, and in the second sort of hour, I will explain that what are the technical tools which are already there, which make it so that if you can justify the trace formula in the case of positive characteristic, then you can go also for the Riemann zeta function and so on. Okay. So I mean, this will be the twofold thing. But mainly behind the scene, of course, what there will be is, if you want, the geometrical framework and the fact that we do have an analog for the Frobenius in general. Okay. And so I will very much insist on the fact that, if you want, now we have really reached a situation where we have this dictionary going on. I will put it there, where instead of just, as in the classical framework, where one has, so if you want, there is a function theory. Okay, and the function theory, as I explained in the first lecture, contains a certain number of items. So the first is like zeros of zeta. The second is a functional equation. So the third is the explicit formulas. Okay, and like the one is the location of zeros. Now, if we look at the case of fields of positive characteristic, we have algebraic geometry. Okay, and we have algebraic geometry over a finite field Fq. So the zeros of zeta get interpreted as the eigenvalues of the Frobenius acting on this étal cohomology, okay, of the curve with LAD coefficients. Now the functional equation, of course, Poincaré duality. Okay. The explicit formulas are just the Lefschetz formula, again for the Frobenius. Okay, and this is like the Riemann-Roch theorem on the square of the curve, sigma cross sigma, essentially. Okay, so now we have a similar framework here, where, I mean, there is, as I said, this is just three things which are on equal footing. I mean, there is no separation between the things. And so what we have here is the Adel class space, if you want, which is, okay. Now, the zeros of zeta, we interpreted them in terms of the eigenvalues, okay, of the action of the ideal class group CK on, so what we had was the difference, if you want, that L2 of CK minus L2 of X. Okay, and there was this delta which we get rid of. Okay, the functional equation is essentially the fact that the map E was satisfying the rule that if you map the Fourier transform of a function at X, this is E of F evaluated at X inverse. Okay, the explicit formulas was just the Lefschetz formula. Okay, again, which is a trace formula. Now, as I will explain, if you can prove the trace formula à la Zellberg, namely with the cutoff and so on, this implies the Riemann hypothesis. And in fact, it's equivalent. Okay, so this is what I will explain. But the most important part today will be the proof that if you have the trace formula, you have the positivity of the Weil distribution. Okay, I mean, this is really what is the most important step. So let me remind you where we were standing last time. So for simplicity, we were looking at function fields. Okay, but this was only for simplicity because most of what I'm talking about will go over with more care. Now, remember that I had chosen a finite set of place S, which was big enough. And what do I mean by big enough? by big enough, I mean the following. I want that, you remember that we had the group of S units, okay, and we had the quotient of the sort of local ideal classes, JS, by the group of S units, okay, and we could identify this with some fundamental domain, which we were taking in the product of the multiplicative group of the fields, okay. Now, the nice property which I want for the set of places to be big enough is the following. You see, I want that if I take the product of D by the, you see, the local units for all places which are not in S. Okay? I mean, I want this to be a fundamental domain for the action of K cross, namely the multiplicative group of the field, on the ideals. J, which is A star, if you want. Okay? Which is GL1 of A, if you want. All right, so, well, I mean, that this is possible is not difficult to see, because, if you want, we are, in all this discussion, it's quite simple to work modulo, as I said, this group U. So locally it was US and globally it was U, where U was the image in the ideal class group of the product of the R star V for all places now. Okay, V arbitrary. Now, this group was an open subgroup of the group of ideals of modulus 1, of ideal classes of modulus 1, and it was a finite index there. That was corresponding, if you want, to the divisor classes of degree 0 modulo principal. Okay, so I mean modulo those which are principal. Okay, so, but I'm talking about divisor classes. So this was a finite group. Now this finite group, we can find a set of representatives G alpha, okay, of this finite group, which are ideal. And these ideals, in fact, I mean, they will be such that J sub V is in norm equal to 1 far enough, okay? So in fact, we can assume that this holds for any V not belonging to S. All right? And we can also assume that the set of places, as I said, is large enough so that when you look at the module of the local ideal class group, it is the same as the module of the field. Now, it's an easy exercise to show that if these two conditions are fulfilled, okay, then what I said is correct. Namely, when you take the product of a fundamental domain here by this product, it is a fundamental domain, okay, for the group K cross. Fundamental domain, I mean that, you know, when you will divide by K cross, in fact, you will have an isomorphism. You see, what I am saying really is the following, that J divided by K cross, okay, is isomorphic naturally to JS mod OS star multiplied by the product of the R star. Okay? Okay, that's what I am saying. But I mean, it's useful to have it, you know, at the level of fundamental domains and so on. All right, so I mean, this is saying that the set of places is large enough. Okay? Now, what we had seen is the following. What we had seen is that we can easily apply the local trace formula that we had proved, okay, to show that if we consider the two projections P lambda and P lambda hat, okay, which correspond to the orthogonal projection on the functions whose support is in the set of X with absolute of X less than lambda, when we consider the local Adel class space, which is XS equals AS divided by OS star. Okay, so that when we project on this and project on the Fourier transform, then what we find out is that we can compute locally with respect to a character of US. So K is a character of U sub S, to U1 if you want. US is a compact group. So what we had done was to compute locally with respect to this projection pi sub chi, what was the dimension of, if you want, well, not the dimension, but we had computed the trace, really. We had computed the trace of P lambda times P lambda hat, the order doesn't matter, P lambda times P lambda times pi sub chi. Okay? And what we had found is that after lambda is big enough, okay, when lambda goes to infinity, this is eventually equal to a very simple thing, which is equal to 2n plus 1, where lambda is a power of q, which is q to the n, where q is the order of the maximal finite subfield. So it's 2n plus 1 times L, where L is the order of the divisor classes, plus L times 2 minus 2g, minus L times F, where F is a ramification of the character chi. Okay? And of course, I mean, it's quite important when you do that that you assume that the character is unramified outside the finite set of places. Okay? I mean, because it's really a character of the local ideal class group. Okay? But I mean, you extend it in a way which is unramified. All right, so this is what we have. And now what I said last time is that on the other hand, we can exhibit very concretely some elements in this Hilbert space in L2 of XS, which are varying according to the character chi, okay, and which have the following property. I will call that psi sub chi, which will have the properties that, of course, because it varies according to US by chi, there is no point in shifting this by an element of US. So in fact, the only elements by which you want to shift it is the quotient of CS by US. Okay? Now this group CS by US is essentially the same thing as the module, okay? But except that it's multiplied by a group of order L, which is a group of divisor classes. All right? Now what will be important is that when you consider the elements of the form mu of G times psi sub chi, all right, when G varies in these classes, this will be linearly independent. Okay? And moreover, the conditions that they belong now to the intersection of these subspaces will be fulfilled provided the norm of G belongs to an interval, and this interval, well, the best is to talk about the log with base q of G, and this should belong to an interval which is minus n plus 2g minus 2 plus f, and interval up to n. Okay, this is what we saw last time. Okay, now the number of elements in this interval is exactly the same as here, and it's multiplied by L because we have this freedom in the quotient, okay, which doesn't depend on the module. Now, for any G satisfying this condition, U of G psi chi will be in the corresponding subspace, namely in P sub lambda intersection P sub lambda at, and these vectors will be linearly independent. So from that, we shall get the following. We shall get that, you see, this trace is, of course, bigger than the dimension of the subspace, which is P lambda intersection P lambda at intersection pi sub chi. Okay, when I intersect projectors, I intersect the corresponding subspaces. Okay? So if I show that this dimension is in fact equal to the trace, I get that all projections commute. In fact, pi sub chi obviously already commutes with the two. And we get that P lambda and P lambda at commute. But we get more than that. We get what is the dimension of the intersection. Okay? And it is exactly what you expect. Okay, so how does one prove that? As I said, I want to be quick. So the way you prove it is very simple. You just take for psi sub chi what are called the elementary functions, namely the functions which, when you work with them, you get the zeta function, if you want, in the Tate point of view. In other words, psi sub chi will be a product, tensor product. I want to write it here. So psi sub chi will be essentially the following thing. It will be a tensor product over the places in S. But of course, then we pass to the quotient in the quotient space. But it will be 1R for the places for which the character is unramified. Okay, as always. And it will be, so V unramified. And for the other places, it will be a chi bar, namely the conjugate of the local character at V, okay, restricted to R star V and 0 elsewhere. Okay? I hope this is clear. Now, what you prove, this is done in the paper, I don't want to spend too much time on that. You prove two things. Okay, first of all, you compute the support of this. The support of this is in R, okay, in the maximal compact subring. So it's obvious that if G has norm not bigger than lambda, than Q to the n, okay, the condition that you have the right support will be fulfilled. Namely, you will be in P lambda. Now, when you compute Fourier transform, there is a loss. First, there is a loss by the genus because of the normalization of the differential idel for the normalization of Fourier transform. So this is how you pick the 2G minus 2. And then there is a loss by ramification of the character. And the reason is that when you look at this local function, it is not very locally constant when the character is very ramified. Okay? So it's very clear that you have a loss. And that loss is proportional to F. Okay? So this is how you pick up these numbers here. And this is how you prove that these are in the correct space. Now, you see, normally, if you were naively computing the dimension of this space, okay, I mean, if you were computing it without having taken the quotient by k cross, you would get a tremendous dimension because it would multiply. Okay, because I mean, at each place you would have a corresponding space and you would make their product. So this would be tremendously large. It would be an exponential if you want. However, because we are dividing by k cross, the u of g which is acting here is only acting by the corresponding idel class. Okay? So in fact, we are just counting the number of elements in the idel class group, which is much, much smaller, such as these sols. And that's why the number is small. Okay? But however, we still have to prove that these vectors are linearly independent. Now, the proof is quite important because it implies much more. So what is the proof? The proof that they are linearly independent is the following. Essentially what you do is the following. You replace this vector psi sub chi, which are in fact only at first, if you want, they are functions on the local space, namely A sub s divided by these local units OS star. Okay? Now you replace them by psi sub chi tensor 1R, namely the characteristic function of the maximal compact subring for all other places. All right? Now when you do that, what happens, because of what we have here, because of what the property of the fundamental domain and so on, is that, well, first of all, the psi sub chi tensored by 1, like that, they are the basic functions which are used. Okay, and in particular what they are cyclic vectors. So they are cyclic vectors for the action of the ideal class group of Ck, now the wall of Ck, on the space which is not L2 delta of x, but which is L2 delta of x, if you want the direct sum of the L2 delta of x chi0, where the restriction of chi0 to the subgroup U is equal to chi. Okay? So I mean, this is the first thing you check, that, and moreover, they are in L2 delta for any delta. In fact, they are in the short space. Okay? All right. So now why are they linearly independent when you pass to the quotient? So what you do is you assume that you have a linear relation in the quotient. So you assume that the norm, the quotient norm, sigma of lambda g u of g psi sub chi, is equal to 0. But remember that this is for the quotient space, okay? For the, namely for the norm which was defined by a sum and so on. Now, if that holds, you can prove that the same holds for this, and when the sum is performed now over k cross. Now, the reason is the following: is that when you perform the sum over k cross and not over OS star, you still have a fundamental domain for the action of k cross here, okay, which is this product. So the sum is very easy to perform, okay, and you can compute it. So you still get the same relation. But now, because this vector is cyclic, if that relation holds, it would hold identically in the full subspace, because the vector is cyclic. Now, if that relation would hold, what it would mean when you go back to the proof of the first theorem, the theorem 1 that we had, that we can characterize the zeros of the zeta function by looking at the image of L2 delta of x inside L2 of Ck, L2 delta of Ck, okay, what you will find out is that this theorem would be false. Okay? And why would it be false? Because you see, all this image of this function would satisfy identically a condition like this. Now, what would this mean? This would mean that they vanish on a set of non-zero measure when you pass in Fourier. Okay? Because this is a polynomial. And the set of zeros of polynomial is a discrete set. So if the product by a polynomial is 0, the function has to vanish on a set of positive measure, and this is not true. Okay, so this is how you get a contradiction. All right, so these vectors are linearly independent, but in fact we learn much more. Because if you look carefully at the formula for the dimension, okay, but very carefully, I don't want to do it in detail. Okay, as I told you, the dimension is 2n plus 1 times L plus L times 2 minus 2G, okay, minus L times F. All right. Now, what do we know? We know that if we look at the proof of theorem 1, not at the theorem, but at the proof, how the theorem was proven, okay, what we had proven, in fact, was that if you take elements which are nicely supported, which are in short space, they are not only orthogonal to the zeros on the critical line, okay, for the corresponding L functions, but they are orthogonal to all zeros, okay, because, in fact, you have a holomorphic continuation of the Fourier transform. Okay, and because they are orthogonal to all zeros, this means that they are, if they are supported in some range, okay, you just have to count what is the dimension of the full subspace here minus the number of linear conditions. The dimension of the full subspace will be 2n plus 1. I mean, character per character, but there will be L characters with restriction to U will be equal to chi. So character per character, it is 2n plus 1, minus the dimension of the set of zeros, the number of zeros of the corresponding L functions. Okay? Now, if you look, for instance, in Weil's book, Basic Number Theory, you can count the number of zeros, and it fits exactly with this formula. Okay? So in other words, we can conclude much more than the lemma. Not only we can conclude that this projector commutes, that we know the dimension of their intersection, but in fact we know much more. We know that this intersection does not change when you increase the number of places. Namely, that if you take this intersection and you make the number of places bigger, it stays the same. The dimension stays the same. Okay? And it stays the same also at infinity. Okay? Namely, at infinity, this argument is a proof that the dimension of what? Of, if you want, the set of psi, such that the support of psi is included in the set of x with absolute of x less or equal to lambda. And the same holds for psi hat. Support of psi hat is also included here. Okay, if we look at this set of psi, and if we take the set of psi which vary according to the character chi, okay, in fact, what I just said shows you that, in fact, we know that space. Namely, what I have described here is the basis of that space. If I take the psi sub chi tensor 1R, so, all right, and the transform by U of G. So you see that we indeed have a complete control on that space, complete control on the dimension of that space. Okay, not only for finitely many places, but for an arbitrary number of places. Okay. So in fact, now I can reformulate both the local theorem, which is proved, okay, in a global manner. I mean, I will first reformulate it locally, because you see, if these projections p lambda and p lambda hat commute, when I was talking about their product, I should replace their product by the orthogonal projection on their intersection. This is much better than to take the product of two projections. Okay? But now what I claim is that the orthogonal projection on their intersection makes sense globally. Okay? And I will write the statement first locally and then globally. Okay, so what is the local statement now? We can now improve considerably the local statement, because instead of making the cutoff in this way, which was, you see, first making the infrared cutoff, then the ultraviolet cutoff, or something like that, we can now make the cutoff in a completely natural manner, which is to take the orthogonal projection on the following functions, namely on the functions whose support is inside, like the ball of radius lambda, if you want. Okay, namely the elements of, well, it's not a ball, I mean, it's the elements of norm less than lambda, and same thing for Fourier. Okay, so that's a well-defined subspace. It is finite dimensional locally, namely it is finite dimensional whenever you fix a character of CK1 or of CK, or of U, okay? And so now if you want, we can rewrite the local statement as the following theorem, that if we look at the trace of Q lambda, so Q lambda is the orthogonal projection, okay? This is the orthogonal projection on the set of psi, local psi's, such that, as I wrote over there, psi of x is equal to 0 for any x with absolute of x strictly bigger than lambda. And same thing for psi hat. Okay? So if we look at trace of Q lambda times U of h, right? Remember U of h was the integral of h of g, U of g, d star g. Okay, so what we know is that this is equal to 2 log lambda, log prime lambda, times h of 1, as in Zellberg, plus the sum over places in S of the finite principal values that we had found, okay, which is the same as the Weil principal value shifted, integral prime of h of u inverse over absolute value in the local field 1 minus u, where this is in the local field k star v, and d star u, where d star u is the normalized R measure, plus little of 1. Okay, so I mean, we know that for any finite number of places. So this is proven, okay, this is proved for any finite set of places. S of places. Okay, but as you can see, the statement of the theorem makes perfectly global sense. Okay, why? Because you see, these vectors, such that psi of x is equal to 0 and so on, they make sense perfectly globally. Okay, they make perfectly global sense. Okay, and they are also defining a locally finite dimensional projection. Everything is fine. Moreover, as I told you, these spaces, very strangely, they stabilize very quickly. Namely, as soon as you take a large enough finite set of places, in fact, the space no longer changes when you increase the finite set of places. Okay? Moreover, if you take the test function h to be a function with compact support, so if you want support of h is compact, okay, and so if it is compact, if you want, it will be contained in the set of variables u, so that u belongs to an interval, I don't know how to call it, C inverse and C, okay, because it's compactly supported. Now, you can immediately check that this sum now comprises only finitely many terms. Why? Because you see, when you take a function h like that, such a function, look at what happens when you take the integral over k star v. Now, the function has to be evaluated on elements in the local field. But elements in the local field have a norm. And this norm, what is it? It is q, namely the common denominator, if you want, to the power of the degree of the place. Okay? But the degree of the place tends to infinity. So in fact, only for finitely many places, q to the deg v or any power of it will be in the support of h. Now, because of the principal value and of the beauty of how it is defined, what you will find out is that if the function h is constant on the elements of norm 1, this integral is 0, so it vanishes. So in fact, this sum has only finitely many terms. Okay? It's also 0 outside a finite set of places. So you know, when you see that, you think it's extremely tantalizing to conclude, okay, that the formula, because neither side seems to depend on infinitely many places. Okay? So what I will show you now, I will show what is the difficulty, however. Okay? But however, let me mention immediately that I can prove this theorem whenever h, so for any h such that the support of h is equal to ck1, namely the ideal classes of modulus 1, the proof of this statement follows from what I have just said. Why? Because the function here is a combination of characters of ck1. Now for characters of ck1, in fact, we have actually computed the dimension of q lambda after a while. And we have found that it is exactly correct. So this means that for any function which in the ideal class group is supported near the identity, okay, in this neighborhood of the identity, it works. This means what? This means that now there is no longer any problem with transversality. because we can handle all the functions which are not transverse, namely all the functions which have h of 1 different from 0, or which don't vanish near 0. Okay? So I will explain what remains to be done. And what remains to be done is to prove it exactly for the analog of the Frobenius. I will explain what is the analog of the Frobenius. Okay? But let's assume that this holds. And let us prove the main result, which is that assuming this trace formula, we get the Weil positivity. So this is really the main result. And I mean, somehow, I believe that, I mean, this is the first proof of Weil positivity over complex numbers. I mean, you know, not using like Castelnuovo positivity or using something like that. We really are handling vector space over C. Okay, and we shall prove positivity of the quadratic form directly. Okay, so I mean, this is really the most important step. So what do we want to do? So you see, first of all, as I just said, the global trace formula now makes perfect sense. Okay? So what I want to do is quite simple. I want to show you that if I assume this trace formula, there will be, of course, a similar trace formula in the case of the Riemann zeta function, I mean, and of ordinary L functions. But this case is particularly simple and nice. So what I want to show is that if we assume this trace formula in the global case, where nothing has to be changed, you see. I have to change nothing. Q lambda is the same. It's orthogonal projection in this space. U of h is our nice U of h. That sum is finite. Okay. Sorry? You remove S, exactly. Okay, so you remove S. So it's for all V now. But the sum is indeed finite. Okay. So let's assume that, and let us prove that the Weil distribution is positive. So what is the Weil distribution? I remind you, as it is in Weil's paper, so the Weil distribution, okay, is the following. It's equal to, okay, what Weil is called like D plus log of D inverse. So D inverse is, I mean, D is a differential del times the Dirac mass at the origin minus the sum of D sub V. All right? And what are these various distributions? I mean, the distribution D is defined by D of F. So it's a distribution, of course, on the ideal class group. By D of F is equal to integral over Ck of F of U times absolute of U 1/2 plus absolute of U to the minus 1/2 D star U. Okay, this is the Dirac mass at the origin, at 1 of the group. And the D sub V, it was obtained by taking this Weil principal value of the integral over the local field K star V. And then what we have is F of U, absolute of U to the 1/2, divided by 1 minus U, V star U. Okay? I mean, this is a Weil distribution as in Weil's paper. Okay? And what does it mean to prove that the Weil distribution is positive? I mean, of course, not that it is positive when the function is positive. It means that it is of positive type, namely what you want to prove. Okay? You want to prove that, so I will call this Weil distribution, I will call it delta of F. Okay, so what you want to prove really is that delta of the convolution of a function with a conjugate function, F star, so where F star of G is equal to F bar of G inverse, okay, that this is positive. All right? This is what you want to prove. Okay. So how will the proof go? I mean, you know, we are now, by now, extremely familiar with this minus sign, okay? Which is the key to the whole story, this minus sign. And we are also familiar with something on which I didn't dwell for any time because it's computation, which I do in the paper. It can be done in 1,000 ways, but which is quite important, which is that if you look at this combination, or rather, if you look at sigma of D sub V, the Weil principal value, minus log of absolute of D inverse times delta 1, okay, if you look at this distribution, okay, this can be written, in fact, as the sum over the places of the integral of h of U inverse, integral prime, of h of u inverse over 1 minus u d star u. This is detailed with utmost details in the paper. I mean, and it's so important because if there was any mistakes there, the whole thing would collapse. So that's why it's detailed in great detail. Now, where h is related to the function f by the following rule, that h of u inverse is equal to, you know, obvious from the formula, f of u times u to the 1/2. Okay? All right, so this is something that you check. So in fact, what we have to prove, if you want, is that this distribution is positive in terms of h or in terms of f. Now, when you write in terms of h, things are much, much closer, I will come back to that, than what they are with the Frobenius and with manifolds. Because you will find that, for instance, when you consider really what corresponds to the Frobenius, which is V of an ideal class whose modulus Q, that's not, sorry, U of an ideal class whose modulus Q, okay, with modulus of G equals Q, you'll find that this operator is not unitary, but it satisfies U of G times U of G adjoint or transpose, doesn't matter, is equal to Q. That's exactly the rule that the Frobenius satisfies as a correspondence. Okay, and it says that it is a correspondence of degree Q. All right, so we shall come back to that. But so far, we can deal either in terms of F or in terms of H. It's all equivalent. All right. Now, what do we know if we have the trace formula? Well, we know that this quantity is appearing here. All right? I mean, this finite quantity of which we want to prove the positivity, or rather the negativity. Okay? You see, what is now in this term the Weil distribution, it's delta of F. Okay, I will switch from F to H, but with this rule, delta of F is just equal to D. But what is D in terms of H? It's H hat of 0 plus H hat of 1. Okay, that's obvious. Okay, this is the first distribution D applied to H, minus sigma over V of this integral prime of H of U inverse over 1 minus U this time. Okay, but this term, we know where it appears. It appears in the trace formula. Okay? Okay. So what do we do now? Okay, let me prove the main lemma. Okay, let me write it here. Okay. You see, remember that we have this map E. Okay, and the map E was an isometry which was going from L2 of x. I could put a delta before, but doesn't matter. I take delta equals 0 now. From L2 of x, 0, namely I had these two linear conditions, to L2 of ck. Okay? And remember also that E satisfies the Poisson formula, namely that E of xi evaluate xi at, sorry, the Fourier transform, evaluated at x is the same as E of xi evaluated at x inverse. All right? Now, this is in a sense the Riemann-Roch theorem. Okay? And moreover, there is a vanishing theorem. Because if, you see what I am claiming is that if psi of x is equal to 0 for any x such that modulus of x is bigger than lambda, okay? I claim the same is true for E of psi of x. Okay, then E of psi of x is also 0 for any x with absolute of x bigger than lambda. And the reason is that E of psi of x was equal to x 1/2 multiplied by the sum of psi of qx. Okay? So obviously this holds. This is the vanishing part of the Riemann-Roch theorem. All right? This statement. Okay. So now let's combine both the Riemann-Roch theorem and the vanishing part to get a fairly non-trivial inequality between two projections. All right? And I will write this inequality over there. All right? So the lemma, the lemma is the following. Okay, so let, now, in ck, let S lambda be the projection, the orthogonal projection, on the functions eta of a needle, j, with eta of j equals 0 for any j such that either absolute of j is bigger than lambda or absolute of j inverse is bigger than lambda. Okay? So let me write the IDEL vertically. Okay? So we consider a cutoff space in the IDEL, okay, which is cutting off all IDEL classes which are either too small or too large. Okay? With the module. Okay, so let S lambda be the corresponding orthogonal projection. Now what I claim is that if we let Q lambda be our orthogonal projection over there, what we have is that E Q lambda, I have to put a 0, E inverse, is smaller or equal to S lambda. Okay? And this is absolutely the key lemma. Okay. So why did I put a 0 here? Because remember that when I wrote Q lambda was corresponding to the space of functions which vanish for x bigger than lambda, as well as their Fourier transform. But remember that we want to be in the short space with two linear conditions. And the two linear conditions are that psi of 0 is equal to 0, and that the Fourier transform of psi at 0 is equal to 0, okay? Which is a codimension 2 subspace. Okay? Okay, so this is the space I consider. All right. Now I claim that if a vector is in this subspace, and if you consider E of psi, it will be in the subspace S lambda. All right? Let me prove it. You see, if psi vanishes for x bigger than lambda, E of psi also. So we are done for the upper bound. Now, if psi hat of x vanishes for x bigger than lambda, we can apply Poisson, and we know that E of psi hat at 1 over x vanishes for x bigger than lambda. So we are done with the lower bound. Okay? But we could do that only because we applied Poisson, so we needed these two linear conditions. All right? Okay, so we get this extremely important inequality. Let me denote by the same letter this new projection Q lambda tilde of 0. You see, now we have this inequality of projections, which is that Q lambda 0 tilde transported by S is less or equal to than S lambda. Okay? Fine. Now, if two projections are unequal, like this, with an inequality, we have a positive operator, which is their difference. That means we can take the operator now, which is S lambda minus Q lambda tilde 0, and that's a positive operator. Okay? Now, you must know the following fact, that the trace of a product of two positive operators is positive. So it follows that if I take the trace of S lambda minus Q lambda 0 tilde multiplied by V, I don't choose U because I am in the space L2 of CK, V of F star F star. You see, this is a positive operator because it's equal to V of F times V of F star. Okay, so this is a positive operator. All right? So now you know that if I take the trace of the product of two positive operators, it's a positive number. That's a very non-trivial fact if you want of operator theory. So this number is positive. But what is this number? I claim that the limit for large lambda of this number is a Weil distribution. Okay? Let me explain why. Because this number comprises two terms. Okay? So this number comprises two terms. The first term is the trace of S lambda times V of S star F. Okay? You see, now I can remove F star F. What I have to prove is that the limit when lambda tends to infinity of the trace of S lambda minus Q lambda 0 tilde times V of F, okay, this is the Weil distribution, delta of F. That's what I want to prove. If I prove that, I am done, okay, because the distribution is positive definite. And it's strangely positive definite because it's a limit of not really subrepresentations, but it's a weak limit of subrepresentation of the regular representation. So it's in some sense using some amenability behind the scene. You see, I'm not constructing the representation as a subrepresentation, but as a weak limit. Okay, the character of the representation. Now, why is that so? Okay, let me just finish there. So the trace of S lambda times V of F, well, this is child play to compute. Because this is a regular representation, and this is a cutoff in the regular representation. So what it is, it's on the nose 2 log prime lambda times f of 1. Okay, this is 2 lines computation of an operator kernel. Okay, so now when you subtract this, the 2 log lambda times h of 1 drops out. Okay, and you remember with minus this. Okay, but you forgot the 2 linear conditions in q lambda 0 versus q lambda, and this is what accounts for the distribution D, which is here. And then you are done. Okay? Okay, so let me stop here and I will start again.